Good afternoon. So today, what we do is a rather very basic thing in processing, let us say, graphs and trees, especially those structures. Important part is which is breadth first, depth first, and its implementation, which uses typically either queue, either recursion, we will see. So last time we saw something about recursion, especially recursion in the tree, and usage of a stack. So we had a stack which is closely related to recursion, and we were able to process the tree using this machinery. Process a tree. Now we will meet another problem, which is not easy to solve either with stack, either with a recursion, and in a moment we will see why, and it will force us to implement a queue. So let's jump into the queue, and that will be it. I have said let's jump into the queue, and they show us a stack. Well, they just recall what's in the stack. The stack is a system where you insert elements from one side. In this case, it is from the left, and again, when you remove the elements, you remove them from the same side, and you've got these operations which have very classic names. When you store anything in the top at the top of the stack, you call that a push operation. When you remove an element from the top of the stack, you call that a pop operation. And when you just peek inside, look what is at the top of the stack, you call that top operation. And when you ask if the stack is empty, obviously the question is it empty? Typically, you don't look inside the stack. That is important to understand that most operations which you do with a stack are just these, and there is no need in most applications to look for something inside the stack. So you are not given typically in most libraries you use, you are not given any method which looks inside into the stack. Of course, you are also not given any method which would change the interior of the stack, because stack, as we will see in a moment, registers what's going on during the algorithm, and therefore you need the information which is there not to be subject to change. So that's the stack. We saw application of a stack last time. So now let us jump into the queue. And as you can see, the queue is a system which is quite similar to the stack. The only main difference is that when you put anything into the queue, then it stays there, and when you want to remove something from the queue, you remove it from the other end. So it works as usual queue for you meet in a real life nearly daily. And now there are similar operations as there are with a stack, only their names are a little bit not that stabilized, not always the same. So you can meet people who will say that they will in-queue something, or dequeue, meaning they're removing something, or they will insert insert at the end or delete from the front of the queue, or they will push and pop and so forth. There is no any general standard in this. So you have to make sure always when you talk about the queue, which operation do you mean. The system is, as you can see, very similar. And now let's see how it works. The problem before we jump into that, just another example how that looks. So. Example of a queue life cycle, a piece of life cycle, of course, just a small snippet of that. What's there? First, you've got the empty queue. Then you insert something, so it's there. When you insert something else, it's being added to the end, and inserting still something more, you add it to the end. When you delete or pop or remove from the front or anything like that, then you remove the first element, which is at the beginning or at the front of the queue, and the rest stays there. Then you insert again something, then you delete front, 11 goes, delete front again, and 90 goes, and then you insert something else, and that it is. Of course, you might say that you don't implement a queue in this way because it seems to be inefficient. Imagine that you have got a queue with hundreds, thousands, millions of elements in it, and suddenly you want to delete front. Then you delete front, and then you have to push all that stuff by one position to the left, and that takes, of course, a long time. So typically, you implement your queue in a different manner, and that is shown on the next slide, which says you have to implement it in a cyclic way. What exactly that does mean, the picture should show. At the beginning, let us have an empty queue, and we will not move the values in the queue. We will only move pointers which point to the beginning and to the end of the actual contents of the queue. So insert something 24, 11, 19, 43, 70. So you insert them one by one as we did before, and you can see the beginning is there, and the tail or the front is on the left, and the tail is just either at the last element or just one position behind it. Does not matter that much. Now, if you go and delete or remove the first three elements, they are removed, and you move the pointer of the front, you move forward. So what happens in real life in your machine is that when you've got that 24, 11, 90, 43, and 70, and there is your front. Front, I tend also to say head, also head, because there is the tail. So when there is some tail, there should be some head of the animal. So there is the, let's say, there is the tail, and now when you pop or remove or delete, remove 24, 11, 90. So what happens is that you do not touch those values at all whatsoever. They stay in your queue as they were there before. The 3, 70. You only and nothing else. You just move your head, front, head is now pointing here. Those values stay there in your in the memory, and you simply do not bother about them. The tail is still there, so they are in fact still in the queue, but they should not be accessible because they are logically out already removed from the queue. So therefore, we don't show them here in these blank spaces, but you might think they are still there. So what's going on next? So we have removed few elements from the beginning. Then we insert some more elements, 10 and 20. And what happens when we arrive to the end of the physical array or physical list in which the values are to be stored, then we again jump to the very beginning of the same structure in the memory and continue from there as if nothing had happened. So after inserting 10 and 20, we have a beginning of the queue here, and the tail is in fact in front of it, and you know that you always have to go forward and then jump to the beginning until you find the tail, if you want, for example, to list everything which is in the queue. And so on and so on. So the cyclic idea should be more or less clear now, and you just have to be careful not to overflow, of course, which happens when now in this but last element the queue is completely full with this implementation, because you cannot move. You say, well, there is a free space. We can put there something. Imagine you want to insert 120 there, but if you inserted it there, then your head and tail would be on the same position, these two green and yellow pointers, but that's the situation which indicates an empty queue when they are on the same position. So be careful when working this way. The next slide shows the implementation of a queue, and as you can see, it is not that complicated. So this is again just not a pseudocode. It is a code, but it is more or less showing you the main ideas. You can use it, but of course you can have queue in your library, whatever language you use. So that's not that important. Just to show that it is easy to manipulate. So what is empty? When the tail is equal to the front, that means the queue is empty. And how do you insert anything into that? Well, what you do, start at the end, take the you are inserting some value. So there you put that value which you are inserting, you put in it exactly at the tail position, and then you increase the tail position by 1. And increasing position by 1 is this rather lengthy statement which says, take your tail, increase it by 1, all right, but what if you are past the end of your of the list or of the file here? So you have to jump to the beginning. Therefore, you have to modulate that value. When you are over, you have to jump back to zero. So this is just a shifting pointer by 1 to the right, and that's it. There is nothing more to do. First, of course, you have to check whether the queue is not completely full. In such a case, you would you need somehow to fix such situation, which we do not include here because that depends on your implementation, and that's it. Deleting from the queue is then very simple. You take front and increase it by 1. That's all you have to do. Of course, again, maybe probably you would say, okay, but what if somebody wants us to delete something from an empty queue? So you might say, all right, and then you would implement another condition that will deny that request if the queue is empty or something like that. These pop and push, they are just renamed other functions. So implementation of the stuff is relatively easy. Queue is relatively easy, and now we come to the problem which forces us to implement a queue. The problem is like the following. We've got a binary tree, which one example is here on the slide, and we want to list all the elements of that tree, which we know we can do by just recursive search using pre-order, in-order, post-order approach or something like that. But in this case, they want us to list everything what is in the tree by the level. So first list the root, then list all nodes which are in depth 1, then list all the nodes which are in depth 2, in depth 3, in depth 4, and so forth. So by levels, which is not supported by the tree structure, because, well, when you come to 12, you suddenly have to jump to 52 into totally different branch of the tree, and you have repeated that in each step. Well, then you have to jump from 52 again, who knows where, and from 82 you jump again to the very beginning on the left. So it's rather complicated. What do? You have to implement the queue like in the following example. Take an empty queue. This is the tree we had on the previous slide. Here is the space for the output, and now we will process it. So the main processing loop says, remove the first element from the queue and process it. Well, so far there is nothing, so we need some initialization, which will obviously happens here. And when we remove that first element, we enqueue the children of the removed element. So let's see how that works. So at the very beginning, we take the root and put it in the queue. So that's the initialization part. And then we can run a main loop. That should be repeated and repeated until while the queue is not empty. So until the queue is totally exhausted. That means when there is nothing else. So it is obvious that during the process the queue will be never empty, only at the very end. So we store the root in the queue and run the loop. Remove the first element and queue insert the children. So let's do it. Remove the first element. Here it is removed. Do something with it. For example, print it. Here it appears. Its value appears on the output, and then we enqueue its children, 21 and 71, in order from left to right. Only those children from 1 to 71, so they appear in the queue, and one loop is done, and we have listed the first level, the level in depth 0. So now we continue exactly as before. Now the whole process becomes completely mechanical. You just take first element, who's that 21, remove it nicely, process it, print it out, and insert its children into the queue. There is only one child, as they said, in queue left and in queue right child, if there, of course, such one exists. So 12 is there, and it is here. Who is still staying there? 71. So 71 will be next to be processed. We have already 3021 here down in the output, so next will be 71 from the right branch of the tree, and that's exactly what's going to happen. You remove 71, 12, which was added there a while before, just stays in the queue. So 71 goes out, and then the second part of the loop, number 1, number 2, you can see you insert those its 2 children into the queue, and there they are. So and so on and so on. So this is repeated and repeated and repeated until you arrive to the very end. So I will skip next few pictures maybe, because they repeat just the same operation again and again. There are so many slides there, just because it was relatively easy to create them with a PowerPoint. So okay, to have some slides, you take one picture, copy it to another, so you've got a lot of pictures. So it continues. I will go to the very end of the process. You can see where it is. Oh, wow. So this is the part which is quite near the end. Who's left in the queue? Originally it was 93, 54, 64. So they are still there in the queue. 93 goes out, and now when any element is removed from the queue, that element has no children. So everything what happens is just removing elements one by one from the queue and printing them out, by the way. 93, so next go 54 out, and finally 64 will go out, which just happened up there, and there it is printed. Now the queue is empty and the task is finished. There are some additional symbols in the slides. Just showing you the structure of the whole process. Sometimes the queue contains exactly nodes of one level, and in all other cases it contains just the nodes from the neighboring levels. In this way, you can look now back what was going on, what is in the queue. For example, you take any situation, 73, 93, 54, 64. So you can see that always in the queue you have just nodes from 2 different depths, at most 2 different depths. It never happens that your queue would contain something. Something like that. So if this is in the queue, this node and this node, so then you cannot have also this node in the queue, or else if you've got this piece in the queue, then already these nodes were removed. Therefore, their children must be also in the queue. So this is queue like this. This is the queue, typical queue contents. So it's a kind of wave which is moving through the tree. The front is moving step by step, and the end is also moving step by step. Now, probably that's all from this part. I think, so what do we need is to say, and sorry, I apologize myself, there is a complicated keyboard here. So the whole process we have just seen is simply sorry, is implemented here quite simply. You create what you create. First, you create the queue with some size. Typically, again, your libraries don't demand you to do that, because they can dynamically expand it if you need it, but that doesn't matter. You create just empty queue. Then you take the node which is which is probably the root of the whole tree, and put it in the queue. And then this loop runs and runs again and again. While a queue is not empty, what do you do? Remove the first element from the queue, process it, that's called node. So then you take key and print it. And what you do next are these two lines. You just take the children, node left and node right, and store them in the queue, which is here called Q. The name Q is also the name of the letter in English alphabet Q. So we use just one letter Q there. So this is the whole stuff, and it really does process your tree, whatever the shape of the tree might be. So it is rather convenient and easy to work with. Now, all right. So that was a tree, and now we are going to do the same method. That means to search, but not the tree. Search the whole graph, which structure might be much more complex than just of a single tree. And we will see that the Breadthfirst search still works using the queue. So let us first look for a while at the graphs. A graph is a system of, as you surely know intuitively and nearly surely know also formally, it's a system of nodes. You can imagine them as a dots of circles in the plane, which are connected by some edges. So typically, to give somebody a graph, you need to specify what are the nodes, also called the vertices, and what are the edges. What are the edges? Well, edges are lines between the nodes, but how do you represent a line where it goes? And sometimes the line is not straight even. You can have something, you can have draw your graphs this way. So how do you represent an edge? You say, that does not matter. It is just a pair of nodes. You just list which two nodes are connected. So if you are, in this case, A, B, C, D, E, F, there are some number of edges, and edge is exactly your pair of nodes which are connected by that line, BD, DF, EF, CE. So if you just communicate to somebody the list of pairs, they are able to draw the graph exactly, not very probably not the same picture, but the same system of connections. So to give somebody a graph, you give them a list of nodes and a list of edges, and they might be quite happy with that. Just a small notice. Typically, I will say nodes. I will not say vertices, because the word nodes is shorter. So when you go implement anything regarding the graph, you tend to use word node, not vertex, because vertex is longer and you don't want to type that much. So we typically use nodes. Vertices is more posh, more theoretical description of this point in the plane vertex. If you want to write a serious book on graphs, you must talk about vertices. You cannot talk about nodes. It's impossible. On the other hand, if you are a practical technician, then you talk about the nodes, and you simply are not afraid that somebody will frown at you. Now there are two important distinct cases or distinct types of graphs called undirected and directed. The undirected graph is just like this one, a system of connections, and if you typically travel between various nodes in the graph, then you can travel in undirected graph. Each edge you can travel any direction, there or back, doesn't matter. In a directed graph, there is a prescribed direction of travel. If you move along or any system or a traffic system or information flow, it happens only in the direction which is given by the edge. You can have in a directed graph such situations, of course, that means you can move there and back. But if you want to move there and back and you have a directed graph, you must explicitly say that we have an arrow there and then another arrow back. So those are edges in directed graph. But how do you list them? I don't like this. There's too much when it is an ordered pair of vertices. So if you communicate to somebody a list of edges in this graph, then you have to say, well, we have ordered list of edges, ordered list of pairs of nodes. So you give them A, B, you give them B, C, and as well you give them, let's have a D there. You give them C, D. And of course, you give them also BA and CB, BA and CB. And that's it, 5 edges. And I also write round brackets. Typically, again, more in mathematics, it is typical that when you talk about ordered pairs or ordered tuples, you put them into round brackets, and BD. A pair, when it is undirected, it is in fact set. So you put it into compound brackets. That's the whole stuff. So if they give you this list, you know you have such kind of graph. Now, of course, this sometimes not always. Sometimes it is convenient to describe the graph, which is of course in fact or not in fact, but it looks like a picture. So you need some more computerish description of the graph. Sometimes it is convenient to store graph not just as a list of connections, but as a matrix. It's called adjacency matrix because it tells you which node is adjacent to which other nodes. So if you list all nodes for example, in the first column and list all the nodes in the first row of a matrix or in the 0th row as you wish. So then you fill the matrix with 0 and 1s, and on particular position you will have 0 or 1 depending on whether the corresponding two nodes are connected. So if you can go from B to C, you put 1 at corresponding position. You can go from B to C, and it is listed here. So there are 1, 2, 3, 4, 5 edges in the graph, and there are 1, 2, 3, 4, 5 ones in the whole matrix. The rest are zeros because there is no connection from C to B, for example. Can you go from C to B? You cannot. There is no that edge. So this is sometimes convenient, but it has obvious disadvantage that it is too huge. Typically, in practical computation, your size of vertices the set of vertices, which is of course the nodes, if that is for example, like 10 to the 6th power, you got a graph with million nodes, which is not too big. Then, of course, your adjacency matrix matrix is of size 10 to the 6 times 10 to the 6, which is something about 10 to the 12. So if you got 10 to the 12, that is something like 1,000 gigabits or maybe, yeah. So it is one terabit, 1 terabit of information, and that is huge, of course. So you don't want to store in your memory such a big structure, because it just takes a lot of space, and you can see that typically there are often many zeros which don't tell you that much. You can go from C just to E, and this zero, when you know that, then these zeros tell you nothing. So it is an important information. So for processing a big graph, it is not good. For processing small graphs, it is sometimes nice. But today we will not jump into adjacency matrices, so I just mentioned them. Very typically, how everybody stores their graph is a so-called list or linked list representation, which works like follows. You create one array or one list of all the nodes, and in each element of that list, you create a reference to possibly another list, and that the other list contains all the neighbors of that particular node. So if you've got E, so from E there are neighbors are B, C, and D. So B, C, and D in any order. That order might be different if typically you don't care on that order. So whatever order there is of those neighbors of E, that will work. And the same happens in all other cases. From A you can go to B, from B you can go to A, C. When you are in B, you can go to A, C, and E to the neighbors, and so forth. If your graph is directed, then you apply the same, absolutely the same idea. For example, in the example we have on the blackboard, let's call this G1. So G1 you would represent as a list of 4 nodes, or just elements corresponding to those nodes, and that will each one will refer to a list of neighbors. Who are neighbors of A? Well, it's only B. The neighbor from B, you can go to A and to C, so it will be A and C there. From C, you can go to B and D. B and D, and from D you cannot go anywhere, so there will be some null reference, or we are in Python, so called none, I think, or something like that. So 1, 2, is it enough? I don't know. There should be 1, 2, 3, 4, 5 references, 1, 2, 3, 4, 5 edges, so that that works. In the case of undirected graph, which is on the screen, you can see that we've got 2, 4, 5 edges, and each edge is represented twice. You can go from A to B, okay, and also from B to A. So you start in B and you can go to A. 2, 4, 6, 8, 10. We have 5 edges and 10 elements in the lists. So this is rather convenient, and we should work with it in our implementation. So, here it is once more. There is a little bit more complicated graph, again represented as a linked list and as a adjacency matrix. Again, in adjacency matrix, you can see that each edge is in fact represented twice. Edge from A to B is represented by this one and also by this one. So again, each information is in the adjacency matrix is inserted twice, but again, in most implementation, that does not matter. So you don't want to cut your matrix in half and use and store in the memory only half of the matrix, because that does does not help that much. Okay, so now we've got a graph here at the top. We can represent it internally by this or by this method. And now we want to go and search it. Search through the graph. That means visit all the nodes of the graph, each one just possibly once, not to be too much chaotic, going back and forth and somehow lost your way in the graph, and do it quickly, efficiently, and that's it. So let us see how the Breadthfirst search, which we have seen how it works on the tree. Let's see how it works on a graph. So what do we? And then so here they show us depth first search. So I will skip over depth first search and go into breadth first search. So first the examples. We will implement a queue and some kind of output there, and we will start somewhere, and all the nodes are green because they were not visited yet. So we haven't seen them. We start anywhere in any node, and the current node which we are working with at the moment is pointed to by this blue arrow. That's it, and there will be some additional values, which are the distances from the very beginning, from the node where we start. We've got this C. You can even imagine the graph to be as a tree with some additional edges here and there. How would you do that? You can say, well, C is at the top, we start there, and there are two immediate neighbors of C, which is F, D, and G, or F, G, and D, the order doesn't matter. F, G, and D. D is connected to A and B. To A and B, and just by some quirk of fate, the A and B are also connected by an edge, but you can, so what? They are connected A and B. F is also, now be careful, F is also connected to G, and G is also connected to D, but that does not matter. So this is the level 0, that's level 1, and then there will be from G you can go to H, and from D you can go to E, from G you can go to H. H, and from D you can go to E there, E, and just again by coincidence, E and H are connected there, so they are in the depth 2. So the stuff we have on here on the slides is exactly the same as the stuff which I've just drawn on the blackboard. The pictures are different. The system of connections is the same. And therefore, you can imagine that we are, in fact, easily implementing a Breadthfirst search, as we have seen in the introductory example. Go through all the levels from left to right and list all those elements. Of course, the small, but maybe not that important trouble is that when you look at this picture, it is not in the form of the tree, but it does not matter. So we can process exactly as we did before. Just take the root or the very first node to process, and then go visit all the neighbors. That is, take neighbor D, take neighbor F, and take neighbor G. This F, G, and D in any order. Well, because you might imagine this is the tree, and the order of children does not matter. Take all of them and nicely store them in your queue. Now C, F, G, and D, F, D, and G were visited, so they are in the queue. C already was processed, so it has been removed from the queue, and because it was at the beginning of the queue, it is printed on its identifier is printed in the output. Now, what do those numbers, added numbers, what do they mean? There is missing at the G, but I hope it does not matter. They just represent the level of particular nodes when you draw the picture as a tree. They just represent the distances from the beginning. So the distances. We will see it in a moment how they evolve. Go to the next slide, and next slide says, well, C is already closed. Then we are processing our queue. So take the first element in the queue, which is D up there, and then just remove it from the queue, print it out, and then insert into the queue its neighbors, but only those neighbors which, of course, were not visited. So there is the difference between the tree processing and general graph processing is that in the tree, we always automatically move to the children. Tree, children, and ren, which have bigger depth. You go to the when you go to the children, you go deeper in the tree. Three children are defined by the tree itself. Itself, they are just one step deeper than you currently are, and it's not a problem to find your children. And you, of course, you don't return back when you are searching the tree by breadth-first search. In a general graph, on the other hand, in the general graph, we don't have any system of children. Who should be children of who? When this is an undirected graph, there is nobody is at the top. Well, we can think that there's somebody at the top, and we can use that information. So we don't have children. We have just neighbors. So it's like more democratic. Everybody is just a neighbor. Just neighbors. Neighbors, so it's just neighbors, and therefore the question is where to go. Visit only fresh, unvisited neighbors. So we must register which neighbors, which nodes, not just neighbors, which nodes were visiting during the search, not to go back to that nodes again. Which nodes has been, it's too long, were visited earlier in the search. And that can be done in different ways. One of those ways is just to assign to each node its particular depth. Before you assign the depth to a node, like we have done in all these examples, before we assign it, the node is undiscovered, the search has not arrived yet to that node, so there is no value. You might initialize it with -infinity or anything like that. So that's just one bit of information which helps you to distinguish between the nodes which were already processed. For example, if you are getting from the very top, you visit C, F, G, D, then you go to H, E, and then you are in A and B. And then, of course, when you are in D, you put those A and B into the queue. When you come to A later, B is still in the queue, but you have to know that B is already in the queue, that it was visited from D, so you don't put it into your queue for the other for the second time. Having this system, we just proceed exactly as we did with the tree. Just imagine the topology is somehow like this, and you do what you do. We have just processed D, put A and B into the queue. They are there, quite happy. We assign also the distances to A and B should be 2. And that's on the next slide. You have to just to imagine the distances of A, B to be there. Probably they were lost in the process here, but here you can see them correctly. So when you process D, what you do, you go to F, which is next in the queue, and when F is in the queue, you look around, and C has already assigned distance. G is already assigned distance, so there is nothing new. So you just take F and say, okay, goodbye, you cannot bring us any new information, and you move to the next element in the queue, which is G, and G has some unvisited neighbor which is called H, so you add H to the queue, print out G, of course. Now H becomes green, that means it is already visited and its distance is 2, and again you have to imagine there is this value of 2. So this works again in the same fashion as it worked before. So you have to go through all elements which are in the queue, and when you come to that element you print its value, and that's all you have to do. Now the queue is empty and everything is done. So that's the whole idea of the Breadthfirst search. Imagine that your graph is in fact a tree with some additional connections, and that's all, and process it like a tree with Breadthfirst search, and easily you can get what you want. That is a walk through the whole graph. There are a few additional slides which try somehow to summarize the whole stuff. So I will show them to you. Here it is again repeated what I have already told you. They talk about open and close times. That is the thing we will come next in the next few minutes when we go into depth first search. So skip this part now. And of course, the result of a breadth first search in the tree. So you just register the distances, and they also tell you when those when the breadth first search is important. So typically, because it is not recursive, as we have seen, you can use it anywhere when testing graph connectivity. Why? When they give you a graph like this one, this is your graph, G2, and ask you if it is connected, and you look at the picture and say, well, it is not connected. There are two pieces, two components which are not connected. On the other hand, if they give you just any description which we have just seen. That is, for example, list of edges. You've got A, D, B, C, C, E, and E, B. So when you are given only this, it's obviously not obvious whether the graph is connected or not, and this is a very small example. So what you have to do when asked if the graph is connected is to implement a search. You implement a breadth-first search. That means you come into any node you choose and run breadth-first search from that node. The breadth-first search stops when the queue is empty, and of course it is because it always moves to the neighbors of particular node. It is only able to process only one component of the graph. Therefore, when you run breadth-first search, it ends, the queue is empty, then you just count how many nodes it has visited. And if it has visited not all nodes, then immediately you know that the graph is not connected. So you can use it for this task. Or you can test existence of a cycle of graph, which also is interesting. Matter how do you check if there is a cycle in the graph. Imagine something like this. Take a tree, which I have an example of in here, and there somewhere inside this stops to be tree. Now there is a cycle in the graph, and you have to decide whether this system is a tree or it's not a tree, or whether that you might decide it by other means as well, but you have to find, when they say you there is a loop and you have to find this cycle, what you do is that you can start in any node, anywhere, for example, there in A, and run BFS, that is run breadth-first search. And running breadth-first search, you can discover this loop. How you do it is that, how you do it? B, C, D, E, F, G, H, I, J, K, L, M, and oh, there's so many nodes. How you do it? If you run a breadth-first search as we did just now, it will assign distances to each node in the tree, and you don't get any more information. That does not tell you if there is a cycle inside or not. But what happens is then you start in A, and then you get to B, and I draw it as a system of levels which contain the nodes in the same distance. So A is in distance 0 from A, B is in distance 1 from A, C is in distance 2 from A. And from C you can go to D, G, and E. So these three nodes are in distance 3, and your BFS will go and discover them. When the BFS will be in E, it will move forward and discover F and assign distance, very probably 4, to node F. Okay, and then it continues, and when it comes to node G, when F is removed from the queue, when it comes to node G will also explore its neighbors, and among others, it will look into into node F, and we'll see that node F already has assigned distance 4, which is bigger than the distance of G. And it will see that that means that, in fact, when you look in some node which already has assigned a distance, that means that you started somewhere. Originally, you came to that node F, in our case, and assigned some distance to it. And after a while, you came to the same node from a different side. And now we are also trying to assign a distance to it. But important part of that is that you are coming to that node for the second time from another side. But you start here somewhere in one node. Of course, those paths by which you got to F had to diverge, and now they are again meeting themselves in one node. So using breadth-first search, you can easily detect if there is a loop in your system, and not just that, you can also then list all the nodes in that loop, which works by, and we don't have it on the slides, I think, which you when assigning this, and then it's to a newly discovered node. What you do is you also register the current node from which you are looking into that newly discovered node. You register that current node as a predecessor of the discovered node. To a newly discovered node, register that is the neighbor of a currently processed node. A new discovered node. When assigning a distance to that node, register this currently processed node as a predecessor of that new one. So we are standing here, discover a new node. Here is the new node which was not visited yet. So from the point of view of that newly discovered node, you say, my predecessor was that node from which I discovered this one. Discovered node. Newly discovered node Z, for example, neighbor of a currently processed node X, register X as a predecessor of Z. It is just the same as we had on this picture. Each node which was visited as a child of some node in the higher level, you will say that H, a predecessor of H is G, predecessor of E is D, predecessor of A is D, predecessor of B is D. So it's the same concept as the children in your tree. So therefore, remembering predecessors is like registering parents there. And when you have the parents, then you, of course, can go along those parents back. And here you can go in one path, in the other path, until the paths do meet. When you go backwards, and there is there you can list the loop. So that is what is bipartite graph. Maybe we will skip it for the moment. We can do it in the labs, because it's a nice question, and typically, finally, here they say that typically also you use Breadthfirst search to calculate the distance in the graph. Of course, because typically what you are given is a terribly complex system of nodes and edges, and you want to know what is the smallest number of edges you have to traverse to get, for example, from B to some other node in the graph, E, F, G, H, I, J, K, from B to H. What is the minimum number of nodes you have to traverse? Of course, you have to assign again to each node its distance. When you are looking for a distance from B to H, you run Breadthfirst search, and that Breadthfirst search also, as a side effect, assign distances to all other to many other nodes in the graph. So you go from B to D. This is in distance 0, distance 1, distance 1. Then this is distance 2, distance 2, distance 2. So now take this, and what is distance 3? This is distance 3, this is distance 3, this is distance 3. So therefore distance 4 is there. Breadthfirst search thus assigns these distances for you to each node, and then you just say, okay, from B to D, from B to H, it is 4. If you are asked how far it is from B to J, you say, it is also 4. But if they ask you how far it is from E to G, for example, then you cannot use the previous information, and you have to run BFS again from E to get to G. So only with given only the distances with given start are of course listed in the result of one Breadthfirst search. So that does the Breadthfirst search. You can see that the implementation is just very similar as we had before. Create your queue. Put there, take the first node in your graph. There is this list of nodes. Take the first one for simplicity and store it in your queue. Tell them that this node was already visited. So you just tick it there. It was visited, and then you go what? You take first node out in the queue in the loop, print the identifier, and then all the either children or not visited nodes, you just store them in the queue. And because you store them in the queue, you have to tell them that they were already visited. So anything you store in the queue, this neighbor, you tell them that you just register it as a visited, and that's all again. One method. Now we've got about 20 minutes to go into the next method, which on the slide is previous method, and that is depth-first search. Depth-first search. First, look at it. The idea is, again, similar to working with a tree, but this time we don't list it along, or we don't visit it along the particular levels. We are trying to first get as deep into the graph as possible, and only then maybe go back. So in trying to do that, there are also not necessary but interesting and sometimes important numbers, which we will just explore now. Start in any node and have a stack, because we are going into the depth, we are going down in the graph, or you might imagine in the tree. What are we going to do is we are just we want to remember the way back to the start, and that is the the role of the stack, which always remember exactly how to get back. So start in a stack, and because we have just started there in C, so we put there number 1 at C. What does it mean? It will be obvious later. Now we move forward along any edge which is available. So for example, it is edge to D. So now we are in D, and because we now discover D as a second node, so we put there at D number value 2 and continue forward. Also, we put D on the stack because CD, now DC is your way back. Continue from D to any node you wish. So here they chose G, so you get to G, and again you discovered G in time, I can say it now, in time 3, so that is third this does not mean it is the third, it's the time of an action. So put there 3. Now, so far, no problem. From G, move forward again anywhere, maybe back, maybe this way, does not matter. Get to H. So on the stack is CDGH. Output is also CDGH. And number 4 is assigned to node H. And continue forward. Now from H, of course, not to go back because we want to get as far as possible. We get to E, and we discover it after 8, so we increase that value 4 to 5, and we are in E now. You can see that because we don't know the structure, and the algorithm, of course, does not know it as well, the structure of the graph, it is not going exactly into the depth. It just moves more or less. In fact, it looks like randomly CDGH. So it was C, D, G, H. So that was it. It has no information about the graph. So it moves there. And now it moves again in the same depth, which does not matter after all. And when it arrives to E, it tries to move again somewhere, but that node already has assigned that green number, so it was already visited. So depth first search says, all right, don't confuse the things even more than they are confused now. Don't go into node which was already visited. Just retract back along the path you have just come to this node, because that was already visited. You will start looping there and never stop. No. Go back along the same path you have just come to it. So you say, okay, that means you take this node E and so-called close it. Say, okay, this is already completely explored. We came to E, we cannot go anywhere else. So say, all right, close it, never process it again, and increase the value which is there by 1 and close it at time 6. So the last event we did something. Increase that time by 1 and add and store it at C. What does it mean? One action is either to discover a new node, and the other action is to say that the node has to be closed, never return back there again. So opening, that's so-called opening, when discovering for the first time a node, you open that node. And when you say, well, there is nothing more to do in that node, you close it. And those are open and close time, and time is ticking step by step, one by one. So anytime you encounter a new node, you increase time by 1 and store that in that node as an open time. When you have to close the node, you take the last time you used, which by coincidence was 5 in this case, and increase it by 1 and register it as a close time of that particular node. So a closed node has assigned to it its close time. Getting that, you move back to H, and where else can you go from H? Nowhere except for going back the same track we came to H. So we also close H, and in what time? Well, in time 7, because the last time anything happened was time 6. So now in time 7 we close H and get back to G. When we are back in G, like in here, we look around and say, okay, we've come from D, we have visited H and everything what's behind, but there is still, we cannot go back to C because that is already visited, but there is still one undiscovered node F. So let's go and move there and discover that node as we did here, and the time of discovery is 8, because last time anything important happened, closing a node was in time 7, so now we increase that, just that value 7 by 1 and store the value in F. So open time of F is 8. Of course, we have just discovered it, so print out the output. And now what happens is that, again, F is the same position as was H a while ago. You cannot go anywhere from F, so you have to go back from F to G, close G, as they see, in what time? Aha, you close G in time 10 because F was closed in time 9 because it was discovered in time 8. So you go back to G. G has, again, no option, so G is closed in time 10. D, still you can move from D somewhere, so you don't close it, move to B. Time of discovery of B is 11 because previously G was closed in time 10. Then move to A, discover A, open time, and close time will be set of A to 12, and then immediately closed in time 13. This will be closed in time 14. As we march back, so A is closed, B is closed times 14, D closed in time 14, and the only thing they can do, move back to C in time 16, and that is all because the stack is empty. Anytime we left a node, for example, where we were in F, where we were in F, we went back to G, and when we were in G, of course, we always are operating in the node which is at the top of the stack. So when we close the node, we also remove it from the stack. That's, of course, important, just to be sure that at the end of the whole process, the stack is completely empty, and we have searched the whole graph, and that's it. Now, why did we do that all? Why did we do that all? There should be some statement about what. This is this one. It is good to know the open and close times, because first of all, just to show it this to you, for example, if processing a tree by depth first search, then you assign these values open and close time to each node, and then you can calculate, when you come to that node, you can calculate how many nodes are there in the whole subtrees of that node. It was open in time 2, and it was closed in time 15, and when it was closed, the algorithm returned back to the parent of particular node, and it never went back to D again. So therefore, everything what was processed and is below D was processed between time 2 and 15. So say 15 minus 2 is 13. Then of course there is minus 1, that is 12. So there are 12 values between 2 and 15, I think. Between 2 and 15, you have 12 other values. and each of those values is either open or closed time for some node. So you take 12 divided by 2, because each node is opened and closed, so there are 2 values at each node. So 12 divided by 2 is 6. Therefore, there should be total of 6 nodes in all subtrees of D. 1, 2, 3, 4, 5, 6. There it is. So if you want to know anytime how big is your tree or big your subtree in the graph, you just perform a depth first search, assign these values to each node, and easily you can anytime later calculate how big are the subtrees. The next usage of depth first search is in situation which is listed down here, and that's the case when you want to know something more about your graph, and typically when you want to check whether there are bridges or so-called cut vertices. Also there is also some name articulation, but I don't like it that much because cut vertex is an easy to remember. Let's put there, bridges, cut vertex, not cut nodes. That's a strange thing. Cut vertices, cut vertices, bridges. Bridges are those edges which when you remove or when you cut that edge, the graph falls apart. The number of components in the graph increases. Now imagine this is the most simple example. There is your bridge in the middle. Remove that bridge and graph becomes disconnected. So those are bridges, and the cut vertices are the same stuff, only it can be a vertex or a node. So there is one cut vertex. If you remove that vertex, again the graph falls apart because there are no additional connections from the left side to the right side. There is another cut vertex, and the end nodes of any bridge which is not connected to a node of depth of degree 1 is also a cut vertex. So there are your cut vertices are there. Remove cut vertex and your graph falls apart. So they are strategically important parts of your system of connection or information flow. Those are servers. If you blow this server up, then your network becomes disconnected, cut vertex. So, and depth first search, strangely enough, I will not present it today, strangely enough, is capable of discovering which nodes are bridges and which nodes are cut vertices. Strongly connected components, well, okay, I will mention it very briefly. When you are in a directed graph, you have the same situation that sometimes you've got such system of connection that your system of connection is made of some kind of islands that when you are inside one island, you can travel there wherever you want. Like in this left one, you can go around and be happy. When you leave that island and move to the other part of graph, there is no way you can back because all the edges which go from this island to the next one, by coincidence, are all in that particular direction. So you say, aha, so it is important to discover these islands of connectivity, which are called strongly connected components. And again, depth first search after slight modification is capable to detect exactly those strongly connected components. So it is useful in many different ways. The complexity, very probably I have to finally mention the complexity. I can skip few slides which are filled with text, and the text tells you more or less everything what we have seen so far. So very probably let's jump to complexity, which is at the end of our slides. Once more go through Breadthfirst search, implementation, remark, it doesn't matter, node distances, asymptotic complexity. Both searches we have seen, depth-first search and breadth-first search, are very efficient. In fact, you cannot have, very probably you cannot have anything more efficient than those. And in general cases, of course, and what do they say here is, of course, this statement, if you go and search the whole graph, which is connected, then your complexity just linearly depends on the number of vertices, of the number of nodes, and on the number of edges. Why they add them here? Well, why they add them here? Because you have to visit all nodes and you have to traverse each edge at least once in any graph. When you search it and you want to search it whole, then you need this number of operations. But please be careful. If you just, for example, look for a distance from A to C in a graph which is, imagine, rather big. So it's big graph. So when you say, okay, we are starting in A, we want to arrive to C, what is the shortest path we should follow, or what's the distance from A to B, then you just run Breadthfirst search, run BFS. You run BFS, and when you run BFS, it starts in A, discovers these nodes, and then it discovers these nodes, and then it stops. Then your program stops it because you say, well, we have just found the desired node C. So you don't run the whole Breadthfirst search through the whole graph if you know that it is not necessary. You just add another condition which will just break the loop, which goes through all nodes, break the loop when you discover the node you are looking for. So in that case, of course, your complexity will not be theta, but will be just only O plus V plus edges, so you don't, of course, go through the whole graph. Otherwise it is exactly this one. If you want to go through the whole graph, why it is so, and there is some analysis which is a little bit worth to mention, because they say each node enters the queue or stack during the search only once, and it leaves the queue stack only once. And while it is sitting in that queue or stack, nothing is happening to that node, so there are no operation with that node. So entering and removing a node to the queue, to and from the queue or stack, takes in total, for each node, takes a constant time. So just constant time, nothing else. You do it with each node, and that means the time spent on those operation is proportional to the number of nodes. And then, of course, when you search the graph, as we have seen, you come to a node, and then you look along the edge into some other node, and when you go back, you simply process this part of graph. When you come back to D, then maybe you might look. You might, no, not always. You might look also forward to more, where to move forward, and among others, you can use that edge for the second time to look in E and say, oh, we don't go to E because it was already discovered. So sometimes you use some edge once, sometimes you use it twice, but not more. Therefore, the number of checking one edge that is going, looking from one node to another only happens as for each edge only happens at most 2 times. So the number of edges tells you how many times you check the connection is between 2 nodes, and that is exactly the second part. The second part of that. The state of the node is tested more times. The number of these tests is equal to the degree of the node. The search tries to access the node from its neighbors, and when it tries to access that node, the node is either fresh, so it moves there, or it is not fresh there, so it does not go there. It tries to go somewhere else. But it was tested. It took some time, but only along one edge. So you've got this. And that would be it for today. There are a few details which I have to move to other presentations. There is a search. I can mention it during the seminars because we will also maybe discuss some more stuff. Especially about recursive searches. So thank you very much, and see you next week.